this video I want to arrive at the first Maxwell's equation. All of them have two different forms, as the integral form and the differential form, and we'll look at both in this video. So first of all, I want to consider a point charge in space. It fills space with its electric field, and the magnitude of electric field is given by Coulomb's law here. I want to consider the electric flux through an imaginary surface with radius little r. I've drawn this two-dimensionally, but in reality it's in 3 dimensions. And I chose a sphere because it has some really nice properties. So let's look at the surface integral. This is over this sphere S, and it's given by E dot dA, and you sum them all up. Now, what's nice about this is that at every point, by definition of the sphere, the radius is going to be perpendicular to the surface. And it being perpendicular to the surface means that if this is the normal vector and the radius are going to be parallel. So their angle is going to be 0, cosine of 0 is 1. So this is just EDA. And I've taken the arrows out to emphasize that those are just magnitude. Another thing that's nice is that every point on the sphere, it's going to have the same r, right? Again, definition of the sphere. And it having the same r by Coulomb's law means that it's going to have the same magnitude of the electric field. So that means that E is constant. So I can pull the E out of this integral here, and I get this. Now what does this say? This is telling me to sum up all the elements dA, all the little surface elements, and when I do that I just get the surface area of a sphere. Well, what is the surface area of a sphere? It's just 4 pi r squared. So I know what E is, that's given here, and I know what the surface area of the sphere is, so I'm just going to substitute. We'll see what happens. We have Q on 4 pi epsilon naught r squared times 4 pi r squared. That cancels with these two, and we're left with Q on epsilon naught. And notice that the r's disappeared, so that implies that I can choose any sphere of arbitrary radius. And also turns out, I'm not going to prove that here, that it doesn't necessarily even have to be a sphere. It could be any surface that I want, as long as it's closed. And this is Gauss's law. For me to tighten this up, this is specifically the enclosed charge. And if I have more than one charges, it's going to be the sum of them. So it's the net charge really that we care about. So here, I can replace that with just the sum of the charge enclosed on epsilon naught. And if the charge happened to be continuous, if we model that as continuous, then that would be just an integral. Now first of all, what is the D field? The D field is actually really the E field times epsilon naught. If you were to compute using the traditional, this being the vector of the partial derivatives dotted with the electric field, if you were to pick any point in space, almost any point in space, you'll actually get 0, which is quite surprising. It seems like the divergence should be always positive. Really actually isn't. And to further make this concrete, we would have to formalize by what we mean by divergence. And actually, you find that it's 0 everywhere, but if you were to consider the point where r is 0, then you run into some problems. It ends up being undefined. So to compute that, we need the formal definition of divergence, E dot dA. Now we worked out what this is. Now I can bring this out of the limits here, and I get this. So 1 on epsilon 0 times the limit, dv goes to 0, of this. Now what is this quantity here? it looks quite daunting, but this really is saying what is the charge divided by the volume. So you know how mass divided by volume is density? Very, very analogous to that. We define that the charge divided by the volume, as the volume of the sphere gets smaller and smaller and smaller, that's actually given the name of charge density. And just like normal density, we use a rho, the Greek letter rho, but we put a subscript v, and that divided by epsilon naught. And if you wanted to get to the traditional here, the traditional with the d in there, let me remind you, the d field, for our purposes, is just epsilon naught times the e field. So I can bring the epsilon naught here, like that, and then I can bring this into the divergence operator because it's a constant, and that, again, by definition, is the d field. That's the differential form of Gauss's law.